recall what we discussed last time, and we introduced the Ampere's law. So who will formulate the statement behind Ampere's law? So why do we need Ampere's law? Why it helps us? If we recall Gauss' law for electrostatics, it allowed us for certain distribution of electric charges to determine in a simple way electrical field. So similar, Ampere's law in magnetism allows us to simplify calculations for determining magnetic field, magnitude of magnetic field vector, in case of certain distributions of uh, electric current. So the formulation of Ampere's laws um, sounds as follows. If we have integral over closed loop for the product, like dot product of scalar dot product of B vector, which is magnetic field vector, and uh, ds vector, some displacement vector along the closed loop, then it will be equal to the product of mu naught, which is permeability of magnetic permeability of free space, and electric current. So this electric current is the current which flows through the area of the closed loop. So based on this statement, we can apply Ampere's law in order to determine magnetic fields of different current configurations. And we considered last time an example how, with the help of Ampere's law, we can determine magnetic field inside a conductor, how it changes from the center of the spherical, like circular cross section of the conductor, and also how it changes outside as we move away from the surface of the conductor. So we have shown, who will recall, how magnetic field changes inside the conductor if we go from the center to the surface. It will linearly increase. It linearly increases because so it goes from 0, which is as the center, reaches its maximum value at the surface of the conductor. And then as we go away from the surface of the conductor outside, then it proportionally to 1 over r squared reduces, proportionally to 1 over r, reduces as the distance increases. So today we will continue application of Ampere's law, but we will consider some special current configuration, which is called solenoid. So it's a system of many coils of conductors, so it's many turns. So we will take into account features of this current configuration and apply Ampere's law in order to determine magnitude of magnetic field, which is created inside such a solenoid. And also, we will introduce the concept of magnetic field flux through some surface. Similar to Gauss' law in, let's say, equivalent to Gauss' law in electrostatics. There we were determining electric field vector flux through some surface, and now we will introduce magnetic field flux through surface. So let me show you some slides. What is solenoid? As I mentioned, it's a system of multiple coils of wire with electrical current. So here we see this cross and dot means current goes into this side, it kind of comes from here, then it repeats because one turn repeats another one. So with such current configuration, it is possible to create inside the solenoid quite uniform and strong magnetic field. So any ideas why we are talking about strong magnetic field for such current configuration in comparison to just a straight conductor with a current?
Because each magnetic field from the
From each turn, yes. So we know that magnetic field is formed perpendicularly to the direction of electric current and to the wire. So we kind of enhance this internal magnetic field with each turn of this solenoid. So that results in the, bless you, that results in the superposition of these contributions to magnetic field, increases magnetic field in magnitude, and also since we have many individual contributions, on average this internal magnetic field inside the solenoid also possesses quite high uniformity. So we can consider it as equivalent to a permanent magnet, because that's something what we have inside the permanent magnet. We have quite uniform magnetic field, and then magnetic lines are come going around. So we can have some equivalence between them. And now we want to apply Ampere's law in order to understand how it is possible to determine actually the magnitude of a magnetic field inside the solenoid. So you can imagine that if we consider Biot-Savart law, which allows us to determine magnetic field vector as vector quantity at any point around the conductor, if we apply that approach and need to take into account each contribution from each turn as a vector sum eventually, and each point, that will be a nightmare because that will require a lot of calculations and quite difficult to realize it. However, thanks to Ampere's law, we can simplify these calculations quite a bit. So let me switch. Okay, so let us consider a solenoid. So here these circles correspond to each turn. Direction of current, so it flows like this, upwards. And we consider this rectangular closed loop. So we place it in that way that part of this closed loop is located inside a solenoid, and another part is outside. So now these are magnetic field lines, which coincide with the magnetic field vector orientation. And let us think how we determine, like how we apply Ampere's law in this particular case. So as you remember, that's integral of scalar product for magnetic field vector and displacement vector, which we choose along the closed loop. So now, if we consider side 2 and side 4 of this closed loop, will it have some contribution to the integral? So we can divide because taking into account that this is a rectangular shape, it's not circular, we can divide in 4 segments this closed loop. We want to get the integral, which is, let me write it down here, Ampere's law statement. So it will be integral over closed loop, magnetic field vector, dot product ds vector. That should be equal to mu naught, oops, sorry, times I. So what is the magnitude of dot product if we have 2 vectors? So magnitude of one vector plus u times magnitude of another vector times cosinus alpha, angle between them. So the s vector will coincide with the orientation of the sides of the closed loop. And now if we consider path 2 and path 4, how they are oriented with respect to the magnetic field lines. Perpendicular, angle is 90 degrees, cosine of 90 degrees, 0. So means that to this integral, these two sides, 2 and 4, will not contribute. Okay, so now another question. If contribution originates from side 1 and side 3, and that's obvious because they are parallel to magnetic field, so cosine 0 will be unity. And in this case, we have just product of 2 vectors, magnitude of magnetic field vector and length of this side 1. That will be contribution. The same will stand for magnetic field vector times length of this side 3, and this is the same length L. So length of these two sides is the same. Will, from your point of view, contributions to this integral along side 1 and along side 3 be the same, or they will be different? So there are just 2 parameters. There is magnetic field vector and length of the segment. So length of the segment is the same. 1 and 3, they have the same length. What about magnetic field? Different, and not just different, but very much different, because only inside solenoid all contributions from each turn, which create magnetic field, kind of enhance each other. Outside, these magnetic field lines are just going in, spreading in the space around the solenoid. So that's why what we can write that magnetic field inside solenoid is much larger than outside. If that is the case, when we calculate this integral, we will have contributions from 2 sides, 1 and 3, and that will be some very big terms plus some very small term, which this small term we can neglect because big is the dominant one, and eventually this integral will come to the product of uniform magnetic magnitude of magnetic field vector inside solenoid times length of this segment 1. It will be L. So let us come to back to our writing board, and we will just write down what we explained. So in this case, integral over closed path for product B vector ds vector of that path which we considered, this rectangular path, will be equal to uniform magnetic magnitude of uniform magnetic field inside solenoid times integral of ds over side 1 of this closed uh, path. And that will be equal to B times L. So we have the magnitude, the result of this integration, and we know from Ampere's law what it should be equal.
Mu naught times
Yeah, times current. So now the question is, what will be the current which flows through the area of this closed loop? The magnitude of electric current which flows through the wire from which we made this solenoid is, let's say, I. That is our current. However, we need to take into account the unique configuration of this conductor and electric current orientation when we want to determine total current flowing through this area of the closed loop. Because what happens here, current passes, this current I which flows through the wire, passes multiple times this closed loop. Means we need to multiply magnitude of electric current in this wire by number of times how many turns are covered by this loop, how many turns fit in the length L. So now we need to write this down. So this will be equal to, let's call it, let's make it more clear. So let's make it as a sum for all currents which are flowing through the area, and this will be mu naught times capital N times I. So I is the current which flows through the wire which forms the solenoid, and N stands to the number of turns which are per length of the closed loop which we consider. Like how many turns go through the area of the closed loop. So now we can rearrange it a little bit in order to express magnetic. So we have left side and right side of the equation. So now we want to write, to express magnitude of magnetic field inside solenoid, and that will be B times mu naught times N times I, and divided by L, which is the length of this side 1 of the closed loop. Now tell me, what is this? The ratio between total number of terms and divided by length of the side. It tells us how many turns of this solenoid fit per unit length. So it's kind of density per unit length, how many turns per unit length we realized with this solenoid. It can be different. It depends how we build this solenoid. If we make big gaps between turns, or we put them close to each other, or let's say we are using a wire with larger cross-section diameter or smaller. So with a small one, we can make more turns. If we pack them close to each other, then we can increase number of these turns, like coils of wire per unit length. So that is important parameter which describes the feature of the solenoid. Because now capital N and L, these are more characteristic of the solenoid combined with the characteristic of the closed loop which we decided to choose. But we can choose any closed loop. So we want to come to some characteristic which is describing the only properties of the solenoid. And that is number of turns per unit length. So we write here mu naught times small n times I. So now we have the expression for magnetic field inside a solenoid as a function of the material environment inside the solenoid, because it could be vacuum, so we have mu naught. It could be some ferromagnetic material. Then here will be also some magnetic constant which will show either so it's diamagnetic or ferromagnetic material. It either increases magnetic field in comparison to vacuum, or decreases magnetic field. So in that case, this part will be uh, characteristic which describes environment inside the volume of the solenoid. So here, with such condition, we assume that we have just vacuum inside. Then we have geometrical features of the solenoid, the number of turns per unit length, and magnitude of electric current which flows through this solenoid. And as you understand, with moderate electric current, because there are always limits how much current we can uh, um, organize flowing through a conductor, because it can overheat and burn. So with moderate magnitude of um, electric current, if we manage to create a lot of turns per unit length, this number is high, we will be able to get, with modern current, quite strong enhancement of magnetic field, specifically inside the volume of the solenoid. Okay, so now let us introduce the concept of magnetic field flux, which is important because that is the first step towards induction, which we will consider next week. So we need to operate with this parameter. So let us assume that we have some surface, and at this surface we can choose some small area dA. So this will be magnetic field vector B, and this will be dA vector. So here we have some angle theta between these two vectors. So dA vector, that is orientation defined by the normal unit vector to the surface element, and magnitude defined by its area. So now, if we want to introduce magnetic field flux, FB will be equal to integral of B vector dot product dA vector. So If we are interested in the magnitude, then we consider, let's say, dFB, like specifically through this small element dA, will be equal to magnitude of magnetic field, magnitude of dA vector, times cosinus theta. So obviously, if angle is 90 degrees between them, the magnetic field flux will be equal 0 if theta is equal to 90 degrees, and dFB will be equal just to B times dA if this angle is equal to 0, if they are parallel, dA vector and B vector are parallel to each other. So the units for the flux of magnetic field, so we see here it will be Tesla times meter square, and since it's such an important parameter for electromagnetism in general, it has some special units, which is Weber, WB. So now, taking this into account, let us determine magnetic field flux through some surface next to the straight conductor with electric field. So this is our conductor with electric current I. So this will create some magnetic field next to it, so we can show it with these crosses. So magnetic field perpendicular, it just from this right side it will enter the plane of the image. So this is B vector, and we choose some area which is placed as like some frame, let's say, placed at some distance c from the conductor. Here we have the width of the frame A and the length of the frame B. So our goal is to find magnetic field flux through the area of this frame. Let's say if the magnitude of magnetic field is uniform, doesn't change with position, then this would be really a simple case, because we would multiply magnitude of magnetic field B, which is uniform in any point within this frame, and would have product of this uniform magnetic field with the area of this frame, which is A times B. However, that's not the case, because we know that magnetic field created by a straight conductor is not uniform. Its magnitude is dropping proportional to 1 over r, which is r the distance from the wire. So that should be obviously taken into account. And why we don't consider it, let's say if it's uniform, why we don't consider any angle? Because we have right angle between the plane of the frame and magnetic field vector. So if we consider dA as its A vector, they will be parallel. So if they are parallel, then we consider only magnitudes of two vectors. In other words, we just multiply magnitude of magnetic field and area of the frame. However, we need to take into account this non-uniformity of magnetic field. So FB will be equal to integral B vector dot product dA vector. And that will be, again, taking into account that they are parallel. We can replace it with just product of two scalar quantities, magnitude and dA, magnitude of magnetic field and dA. B is a function of position that we need to take into account. So we know the expression for magnetic field created next to a straight conductor. That is mu naught times I divided by 2 pi times R and times dA. So that is our integral, and here we need to make a transition. So we need to represent dA in form of dr in order to be able to do the integration. So any suggestions how we do it? So let us consider small area within this frame. So this is our area here, and this is dA. dA can be represented as B, length of the frame, times dr, like small distance along the frame in this direction of the shorter side of the frame. So we can write that dA will be equal to B times dr. So we will substitute it in our integral. So it will be mu naught times A over 2 pi r. Instead of dA, we have B times dr. And now we can factor out from this integral all our constants. So it will be mu naught times I times B divided by 2 pi. And under integral, we will have dr over r. Here we also need to define the range of integration, because we need to integrate for all area of this frame. So what will be the range for integration here? From where to where we will integrate?
From C plus C plus A.
Exactly, from C to C plus A, or A plus C. From C to A plus C. So what do we get here? It will be mu naught I times B over 2 pi times natural logarithm of R from C to A plus C. And that is equal to mu naught I times B over 2 pi. Then we have natural logarithm A plus C minus natural logarithm of C. And what is the difference of logarithms? Gives us logarithm of the ratio. So we have mu naught times IB 2 pi in the denominator. And here will be natural logarithm of A plus C over C. And eventually we write that it is equal to mu naught times IB over 2 pi natural logarithm of unity plus A over C. And this is the magnetic field flux through this frame placed next to a straight conductor with current I, and obviously taking into account the non-uniformity of magnetic field, which is created by this conductor with electric current. What is important to mention here for your understanding, that let us recall what was the statement of Gauss' law in electrostatics, that flux of electric field vector through a closed surface, so that is the key moment, closed surface, will be equal to the product, to the ratio Q divided by epsilon naught. And Q is not just some charge, is considered from physical point of view as the source of electric field, because charge is the source of electric field, it creates electric field. So taking this into account, so for electric field vector, the flux of electric field vector through a closed surface will be equal to the amount of the quantity of electric charge which is enclosed in this surface, and electric charge is considered as the source of electric field. So now let us think about magnetic field. We can also calculate integral, like over closed surface, like find flux of magnetic field vector through a closed surface, and think what it will be equal to. So if we draw some analogy with electric field, in the right side we have some source of electric, which is enclosed in this surface. What about magnetic field? Do we have source of magnetic field? As an elementary equivalent of charge, because the source of magnetic field is the mobile charges, like flux of charges. But we do not have like elementary source of magnetic field, because we discussed at the beginning that no matter how we divide magnets, we will not be able to get separately north and south pole of magnet. They will always rearrange, and if we divide it in half, in the smaller part we will have also north and south poles. So that means there is no known to nowadays science source, like unipolar source of magnetic field. Means that magnetic field lines, as we also discussed previously, they do not originate at North Pole. They go out from North Pole and they go in the South Pole. So similar, but fundamentally different, happens with electric charges. We were telling that electric field lines originate at positive charges and terminate at negative charges. So we have really distinct source of electric field lines. For magnetic field, we don't have, so we have only closed loops of magnetic field lines which come out from North Pole and go into South Pole. If there are no such equivalent of magnetic field source as electric charge is source for electric field, there is nothing to be in the right side of this integral. So that's why we can write that the integral over closed surface of magnetic field vector dot product dA vector will be always equal to 0. So no matter what, magnetic field flux through a closed surface will be always equal to 0, and that is a condition which is can be very useful to some further applications in field of electromagnetism. So let us summarize our discussion for today. We recall the formulation of the Ampere's law, and based on this law, we determine magnetic field inside the solenoid. So we didn't do this multiple calculations of magnetic field vectors with Biot-Savart law. We just applied Ampere's law, and that allowed us to determine magnetic field in solenoid, which is a special configuration of electric current when we can significantly enhance magnetic field inside this structure. Also, we introduced magnetic field flux, which is measured in Webers, and calculated magnetic field flux of magnetic field created by straight conductor with current I through a rectangular frame placed at some distance from this conductor, taking into account non-uniformity of magnetic field distribution next to the linear source of magnetic field, which is a straight conductor. So with this, we are equipped already to proceed further in introduction. I introduce induction part, which will we start next Monday. So I wish you good weekend. Thank you for attention and see you next week.